In the last few videos, I talked about assessing the fit of a multiple linear regression model. And in this video, I'll talk about the regression model assumptions that underlie the multiple linear regression model. These are very similar to the assumptions that we talked about with simple linear regression, only now because we have more than one predictor, things get a little bit more complicated. So those four assumptions are about the random errors in the model, which are defined as the difference between y and the expected value of y, or given by this formula y minus b0 minus b1 x1 minus all the way up to minus bk xk. So the first assumption is that the probability distribution of the random error at each set of predictor values has a mean of 0, and this is sometimes referred to as a linearity condition or assumption. Next assumption is that that probability distribution has constant variance at each set of predictor values. Next assumption is that that probability distribution is normal at each set of predictor values. And then finally, the value of the random error for one observation is assumed to be independent of the value of the random error for any other observation. So how do we go about checking these assumptions? Well, we do the same thing we did with simple linear regression, only now we have many more plots to look at. So the first step is to calculate the residuals, which are the differences between the observed response values y and the fitted response values y hat. And then we can draw a series of residual plots. And residual plots have the residuals along the vertical axis and some function of the predictors along the horizontal axis. So for example, along the horizontal axis we can plot the fitted values from the model y hat, because that's simply a linear function of the predictors, or we could plot one of the individual predictors. And we can consider both predictors that we've included in our model and also predictors that we've excluded from the model. And we'll see an example of this in a few slides. So once you've got your residual plot, you assess three of the assumptions using this residual plot. So we can assess the zero mean assumption or the linearity assumption by asking the question, do the residuals average out to 0 as we move across the plot from left to right? And I'll be a little more explicit about that when I go through the example. We can also assess the constant variance assumption. So is the vertical variation of the residuals similar as we move across the plot from left to right? And we can assess the independence assumption by asking ourselves, do the residuals look random with no systematic patterns? It's a little difficult to assess the normality assumption using one of these residual scatter plots. So instead, we can draw either a histogram or a QQ plot and ask ourselves, does the histogram look approximately bell-shaped and symmetric? Or, a little easier, do the QQ plot points lie close to the diagonal line? So here's a series of residual scatter plots where everything is fine. If we were to assess the zero mean, constant variance, and independence assumptions in all of these scatter plots, we would determine that there's nothing to worry about. And it's important here to not get too stuck on very subtle patterns, because it's easy to let your mind be overinterpret these plots by finding patterns and thinking that, oh my goodness, there's something going on there. But in reality, you're just looking at random data, and all these data were generated randomly, so it really is random data that we're looking at. So there's nothing to worry about in any of these plots. By contrast, here are some plots which would fail the assumptions. So in the top row, we're failing the zero mean assumption, because as we move across the plot from left to right, the mean of the residuals is not staying close to that 0 line. It's got a U shape here, it's got an N shape here, and it's got an up and down and up again pattern in this one. In this next series of plots, these plots are violating the constant variance assumption, because the variability of the residuals as we move from left to right increases in this plot, decreases in this plot, and then starts high, gets low, and gets high again in this plot. These three plots here, these fail the normality assumption. These two plots here, you can see that the residuals are skewed. This one, it's kind of subtle, but we've got too many points too close to the line, to the zero line, and a few that are really far away. So this one, it's a more subtle violation of the normality assumption, but it does violate the normality assumption. It's easier for these three plots to actually look at QQ plots or histograms, and we'll do that on the next slide, next two slides. And then finally, this last row violates the independence assumption. In this plot here, the residuals are tracking each other too closely. This one, there's too much of an up-down pattern. So in this one, these residuals are positively autocorrelated. These ones are negatively autocorrelated. And in this one over here, we've got this strange smiley face pattern that's clearly not random. Here's some histograms where the upper three pass okay. And again, you might look at, say, this histogram and go, well, that doesn't look very normal. It doesn't look like a nice symmetric bell shape. But it's good enough. It's close enough. These bottom three fail. These two are obviously skewed. And this one, it's more subtle, but this is where we've got too many residuals really close to zero and a few that are really far away. So it doesn't have this bell shape that we're looking at. It's too kind of tall and skinny in the middle and with these big fat tails. QQ plots perhaps a little easier to look at visually. So the top three pass okay, and again, you might be looking at, let's say, the middle one and going, well, we've got these points here and these aren't on the line, and these points up here aren't on the line. I'm not sure this is normal, but these data were generated from a normal distribution. This one is perfectly normal, and you're just seeing sample variation. The bottom three are the ones that fail. These two, this one in the middle, this one on the right, clear signs of skewed distributions. And this one here, this is the interesting one, where it was a little difficult to tell from the histogram that it's not normal, but you can see from the QQ plot that these points in the tails are way off the line. Okay, and this is enough for us to determine that this isn't normal. So, assessing these assumptions in practice, it's difficult, tedious, time-consuming, and it relies on making decisions, very subjective decisions, so it can be frustrating. So take your time. It's worthwhile because the more assumptions, the more evidence we can gather that the assumptions are okay, the more we can rely on our modeling conclusions. Where you want to perhaps pause and say, okay, this is something worth worrying about, is where you've got a very clear violation of one or more of the assumptions. Okay, anything that's not super clear, is not jumping out at you, it's really not worth getting too excited about, because it's very easy to look at a residual plot and think you see something, but in reality you're just seeing random variation. So only get excited if there's very clear patterns that would indicate violation of one or more of the assumptions. Remedies we'll talk about in chapter 4. For now, one remedy is to just try a different subset of the available predictors, and we'll see an example of how we can remedy a problem in the example that I'll run through in the next few slides. One thing that's a little bit reassuring here is that regression results tend to be quite robust to mild violations of the assumptions. So as long as we're not violating the assumptions too much, we can usually get away with it. And another caveat that we came up against with simple linear regression is residual plots can be quite difficult to use either when n is really, really small, or conversely when n is really, really big. So residual analysis of the type that we're talking about here works best in moderate sample sizes. Okay, so let's work through an example. So I'm gonna work through this in R. So I've got some data here, and we'll just take a quick look at it. You can see we've got a response variable y and 3 potential predictor variables x1, x2, and x3. And this is just data that I generated randomly. Not wholly randomly. There is a relationship between y and the x's. Let's suppose we start off by fitting a model where we just use 2 predictors, x1 and x2. So I'll fit my model, and then I'll draw a residual plot. So the residual plot has residuals on the vertical axis, and it has some function of the predictors on the horizontal axis. And in this case, I'm actually going to look at one of the predictors that I haven't included in my model yet. Okay, remember my model just includes x1 and x2, but I'm going to put x3 on the residual plot. And the reason I'm doing that is because if I find that there's a relationship between the residuals and x3, that suggests that that predictor x3 could help explain some of the unexplained variation in my model, because the residuals are picking up the unexplained variation. And so if x3 is able to explain some of that unexplained variation, perhaps it could be put in the model and it would be useful. So in particular, what am I looking for here? So I'm going to focus on the zero mean assumption at the moment. So let me just make this graph a little bit bigger. So let me zoom into it. Okay, what I've got on the graph here is I've got this line here, and this is a low S smooth of the data. It's a line that tracks the trend in the scatter plot, and it's not constrained to be a straight line. It just tracks the trend. And what it's showing me is that as I move across the plot from left to right, the average residual, which is tracked by this trend line, this low S smooth, is increasing. And that's a violation of the zero mean assumption. The zero mean assumption says that that average, which is being shown by this low S smooth, should be 0. It should be just a horizontal line close to 0. But instead, it's a positively sloped line. The average residual tends to increase as I move across the plot from left to right, and so that zero mean assumption is violated. So the low S smooth is a useful addition to a residual plot. Helps you assess the zero mean assumption. Let's just look at that in a little bit more detail so we can see exactly what's going on. So this is just that residual plot again, only this time I've got these red vertical lines just dividing the plot up into vertical bands. And this is something I talked about when we talked about checking assumptions in simple linear regression. I talked about how in a residual scatter plot, one way to assess that plot in terms of the zero mean assumption is to fix the value of x3 in this interval here. So I'm just focused on the residuals in this band. Ask yourself, what is the average residual of the residuals in this band? So I'm thinking about these points here, where the average residual is down here somewhere, okay? And that's what the low S smooth is tracking. If I move to the next band, I'm thinking about the residuals in this band and asking myself, what's the average residual for these points? And it's about here, right where the low S smooth is. And then in this band, I'm doing the same thing. what's the average residual for these points, what's the average residual for these plotted points, it's right around here. Okay, so this low S smooth is doing that kind of slicing into bands and considering the average residual, but it's doing it in a transparent way. It's doing it using kind of fairly sophisticated modeling, but it's doing what our eyes are also doing. So this is how that low S smooth helps us assess the zero mean assumption. Okay, so we've kind of dwelt on that long enough. We've decided that the zero mean assumption is violated for this plot. So this model that we fit can't really be relied on. It's not satisfying one of the assumptions, and so that's enough for us to say, okay, well, maybe we can improve on the model and find a model that does satisfy the assumptions. So the obvious thing to do here is, because we've discovered a positive relationship between the residuals and x3, let's put x3 into the model now. So let's fit this model, model 2. And let's take a look at the scatter plot with the residuals and x3, see if things have improved. So if I zoom into here, yeah, clearly things have improved. Now this low S smooth, which is tracking the average residual across the plot from left to right, it's very close to being zero all the way across the plot. I don't have any worries about the zero mean assumption. If I was to do this kind of by eye, I would do the same kind of slicing and averaging technique and come to the same conclusion. Okay, so we're good on the zero mean assumption for this plot. What about the constant variance assumption? Well, let's go back to the zoomed in version. And now in each slice or each band, I'm thinking about the variation of the residuals, and I'm asking myself, does it remain constant from one band to the next band, or from one slice to the next slice? I think it does. It's kind of, this is the variability here where I'm moving the mouse. This is the variability. It's perhaps a little bit smaller in this band, but it's not really that different. This one, it's perhaps gone up a little bit more, but it's again, it's pretty good, pretty close to being constant. It's only perhaps in this last band where things narrow, but there's only 3 points here, so I don't have a lot of information about that last band, so I'm not going to get too excited about it. Okay, over thinking about the plot as a whole, the variation stays constant as I move across the plot from left to right. Okay, and then the other thing that we need to be checking here is independence. Just kind of looking at the plot as a whole, do I see any clear non-random patterns here? Well, nothing's jumping out at me, so independence is probably fine. So that's the residual plot with x3 on the horizontal axis. To have confidence in my model, I need to look at a whole series of residual plots. Ideally, one for every predictor in the model, every predictor that I've perhaps excluded from my model, and the fitted values. And if I look at all of those plots and assess those 3 assumptions, zero mean, constant variance, and independence for all of those plots, I'm going to be pretty confident about my model. We'll come to normality in a second. Okay, so let's look at the plot with the fitted values on the horizontal axis. Okay, I've got the low S smooth here again to help me with my zero mean assumption. Stays pretty close to 0, it's good. Variability across the plot is good. No strange patterns that suggest independence, lack of independence. Okay, let's look at x1 on the horizontal axis. Again, zero mean, constant variance, independence all look good. There's x2 on the horizontal axis. Those 3 assumptions all look good. and there's x3. We've already spent some time with x3. Okay, so for all of those plots, all three assumptions look pretty good. We're in good shape. The only thing we haven't checked yet is normality. So let's look at normality with a histogram. Symmetric and bell-shaped. Yeah, good enough. Little easier. Let's look at a QQ plot. The points lie close to the diagonal line. Yes, they do. Normality is good as well. So in summary, what we just did was we fit one model, looked at a residual scatter plot, and determined that the zero mean assumption was violated. And so we threw out that model and said, okay, we need to improve the model. Let's try adding x3. Then we fit that model, did another residual analysis, and concluded that all four assumptions seem to be reasonable for this model. Okay, so that's an introduction to assessing the assumptions in a multiple linear regression model. In the book, I do also talk about assessing the assumptions using a variety of numerical tests. And so that's another way of obtaining evidence that the assumptions are either reasonable or likely to be violated. And I'm not going to talk about that here, but I do talk about that in the textbook.